This is the first of several segments on ethological concepts, and I think what you'll find as a common thread throughout these segments is the importance of animal signals and responses.
Here, a blackback adult is drowning a young herring gull that it knocked out of the sky. He feeds the whole chick to his own young, now old enough to pull it apart themselves. Half of all chicks hatched on Appledore die before they can leave the island. The half that survive carry the genes of parents who are effective foragers and effective communicators. It's those genes that have survived, and those genes that will be passed to future generations. The signals are older than the species. The displays evolved millions of years ago in a common ancestor, accumulating in the lineage when various movements, cues, and sounds became the ritualized, stereotyped displays that we see today. Over time, gull species have diverged, but the complement of behaviors has remained relatively unchanged. Evolutionary history means nothing to the individual gulls on Appledore. They need to communicate to find a territory and a mate, and to successfully raise offspring that carry their genes. Each generation must master the use of these signals, when to employ them, when and how to respond. Effective communication is crucial for survival, and communication begins with a signal.
So in this first segment, we're going to focus on stimuli, but before we get to that, I just want to give you one term. It's called an ethogram, which is basically a catalog or inventory of the species-typical behavior of a particular species in natural conditions. So it's not always going to be complete. It's not always possible to collect every possible bit of data that captures every single behavior that an organism does. But people do try very hard to put some of these things together. Let me just give you a couple examples. So here's an ethogram on bicolor damselfish, and you can see that he even uses the word down here, the ethogram, looking at various motor patterns, types of movements, species-typical movements, color patterns of these animals that serve as signals to other animals, the kind of sounds that they make in communicating. So a lot of information in this monograph. Here's another. This is another monograph on black rats that are in the wild, and you can see that this investigator is looking at a variety of behaviors, social interactions, courtship and mating, displacement behavior. We'll see what that term means in an upcoming segment, and all kinds of parental behaviors and caring for the young, as well as even learning, problem-solving behaviors. Here's one on free-living chimpanzees. I believe this is Jane Goodall's very first scientific publication, and she spent so much time studying these chimps, and this was back in 1968. Obviously, she spent a lot of time since then, but you can see a lot going on in terms of describing the kinds of things they do, and this table of contents you're seeing here is only partial. What else do we have? Oh, feral domestic fowl. These are the word feral means they're domestic animals that have been turned loose in the wild. Instead of being studied in a barnyard, now they're studied in the wild. And so now we're trying to get a handle, or these investigators were rather, on the kinds of species-typical behavior of domestic animals when placed back where the wild progenitors are found. And again, you can see that there's a lot on social behavior and communication and all sorts of other species-typical behaviors. And this one is on the India hill myna, which is a great vocal imitator. So this one does focus only on the vocal behavior, but again, a pretty thorough ethogram of the vocal behavior of the Indian hill myna. So now we're going to look at stimuli, and basically what we're going to be focusing on are the different categories of stimuli when we describe species-typical behavior. You could think of it in a way as kind of like a vocabulary that ethologists use when talking about different types of stimuli. The broadest category is sign stimulus. Any stimulus that evokes species-typical behavior. It doesn't matter if it comes from a conspecific, which means a member of the same species, or a heterospecific, a member of another species. It doesn't matter. This is the broad category, sign stimulus. What will matter is when we break these down into whether we're dealing only with signals that come from a conspecific. But for now, any stimulus at all that evokes species-typical behavior is a sign stimulus. So here's an example. So there is the red underside of this stickleback, a European fish, very small fish. And that actually evokes aggression on the part of another male. Or you've already seen what this is all about, the red-winged blackbird and the red epaulets, the importance of the fact that they're red in setting up and then maintaining a territory. So basically it is an aggressive signal, keeping the other males off the territory. Even sounds are sign stimuli. These are called seat alarm calls. And no, that's not a misspelling. There are 3 E's there. It's just sort of a way of describing what the calls sound like. And you're looking at 3 different species here. So that's basically what it sounds like. And you can see that the sound spectrograms are very, very similar. So these seat calls work between species, and they're used as alarm calls when any of these species spots a potential threat. Like my dog barking in the background, for example. This is another sign stimulus, and I think you'll see that it works very well between species. There's a bat, African gray parrot, chimpanzee, human. And there's a good chance you're yawning right now just because you're watching this kind of thing happen. It's called contagious yawning, a very potent sign stimulus.
Have you ever yawned because somebody else yawned? You aren't especially tired, yet suddenly your mouth opens wide and a big yawn comes out.
And even that cartoon might cause you to yawn. Even if I put the word yawn up there, that might cause you to yawn. So this is a neat experiment. This is a video of this chimp that is yawning. Now this chimp is watching the video of the other chimp yawn. Watch what it does. You can see the video. Watch that chimp over on the right. And it's going to yawn too. Contagious yawning is not something that only includes humans. And like I said, it works very nicely across species. Here's a study that was done with dogs and humans. So that was the dog yawning. What was really done in this study was humans yawning and whether that would cause a dog to yawn. So here's how it was set up. Pretty simple, actually. A human yawn or a human mouth open. Okay, now that's me, but I did not do this study. The people that didn't provide photos in their research article, or at least not good ones. So that's a real yawn. I am actually yawning over on the left, and I just have my mouth open on the right. So, were there differential responses in the dogs viewing photographs like this? Absolutely. They only yawned if they saw photos of a human yawn. Not a single dog yawn occurred if they just saw a human mouth open but not yawning. Okay, here is a special kind of sign stimulus. It's called a configurational sign stimulus. Configurational is kind of the key here. It's a sign stimulus, the effects of which depend on the relationships between its elements, the configuration of its elements. So that sounds very confusing. I hope it won't be. This is a configurational sign stimulus. It's a silhouette What on earth is it? Well, it depends which way it moves. And in this case, that's the configuration, the direction of movement. If it moves this way, it looks a little bit more like a goose because geese have long necks and short tails. If it moves in this direction, it looks more like a hawk because hawks have short heads and long tails. So the experiment here is to actually fly this over a bunch of nestlings and see what they do. If it's flown in the direction of a goose, which is a non-threatening stimulus, nothing happens. If it's flown in the direction of a hawk, they hunker down in the nest, trying to hide from that threatening stimulus. A configurational sign stimulus. The configuration here is not the shape per se, but the direction in which that silhouette moves. So here we have some birds gaping, and you can see the parent has just arrived back at the nest, about to feed it. And typically what will happen, as soon as the parent just arrives, that's going to get them gaping. So that's what we're dealing with here in terms of a configurational sign stimulus. If you think about the shape of a bird, an adult bird, the body is larger than the head. Okay, so this again was done with silhouette models. So what they did was take the model over on the left, which conforms more to the configuration of an adult bird. And then over on the right, they just rotated it around so that it doesn't conform to that configuration and presented these at the nest of nestlings. And they found that when they used the configurational sign stimulus on the left, the birds indeed would gape. If they used the one on the right, they would not. They just ignored it. Configurational sign stimulus. Now, here's another type of stimulus, a releaser. This is a conspecific sign stimulus. So these only work among members of the same species. Each individual nestling of any given species has unique gape marks that are typical of members of that particular species. And parents will only feed the chicks that have the appropriate gape marks, meaning that they're assured that they're feeding members of their own species. So we're looking at gape marks of different species here. And some are on the tongue, they're different colors, but they're also different shapes, different configurations, 3 different species, releasers within each species. So basically, the parent of that species will not be dropping food into that species or that species' mouth. Another releaser, again, a subcategory of sign stimulus, ones that work only among conspecifics. This is called the dewlap display, which is found in lizards. This particular species is the anole or anolis lizard. And they use this to threaten other males as well as to court females. That's typically the function of the dewlap displays, but it only works within members of the same species. Here's another species of lizard. This is called the flying dragon. You can see it's a very different type of dewlap display, which will be totally ineffective if viewed by an anolis, just as the flying dragon would ignore the anolis dewlap. And greeting ceremonies that release pecking by chicks. Okay, so what we're going to see in this brief clip is the arrival back on the home territory of a gull. And you'll see the gull adopt a particular posture and then watch what the chick does, or chicks do. There's our returning gull. Greeting posture. There's 2 chicks going over to that gull that just returned. Well, actually, only 1 chick is doing it. And pecking its bill. That will ultimately cause that adult bird to regurgitate food for the chick on the ground. Now, ultimately, that other chick did the same thing. I just shortened this clip. And we'll be looking at that in more detail. But first, nod swimming. Nod swimming by female mallards is actually a releaser that causes the males to now engage in one of the three major courtship displays. Either the grunt whistle, the head up, tail up, or the down up. Now, sometimes they'll do that if she doesn't not swim. But typically, if she does not swim, and typically she would do that like in a semicircle around a group of males, then the males will do one of these three displays. I mean, different males might do different displays. There might be some that grunt whistle, some that do the head up, tail up, and so on. But nonetheless, it does serve as a releaser when done by a female. Okay, here's another type of stimulus. This is a supernormal stimulus. It's an artificial stimulus, okay? It's totally artificial. It's human-made. But it's better, it's superior to a natural stimulus. And so the whole reason why ethologists construct supernormal stimuli is to actually try to see what animals are responding to. What features of the natural stimulus are they responding to? So here we obviously have a supernormal stimulus, a field experiment done by Nico Tinbergen. And it's basically a papier-mâché, very large egg that he's placed in the nest next to the smaller natural egg. You know, he wants to see what matters. Is it the coloration, the speckled coloration of the egg, or is the gull paying more attention to the size of the egg? What's going on here? And it turns out size is what matters. They will preferentially ignore their own egg and instead try to incubate this papier-mâché egg because it's larger. So size is important as revealed by this supernormal stimulus. This is a wood pigeon, and you see some white markings on the pigeon. You see some white markings on its neck right there, and you see some along the wing. Well, this study used supernormal stimuli to see whether or not the wing white marks played any role in terms of affecting other members of the same species. And there you can see, again, they're more prominent from this view and from that view as well in this individual. These are all wood pigeons. Okay, wood pigeons. They are a different form of pigeon than what we have around in New England. Anyway, so here's what they did. So they made some models, and here they only have a ring on the neck and a larger ring on the neck, so it's a supernormal ring on the neck. This one doesn't even look like a pigeon. It's just a control. It's just a black circle. That one has no white on it at all. Now we're looking at white on the wings, various wing marks with white. Then some supernormal stimuli, the two over on the right, because normally there's only one white bar, and this one over here has two, and then a really thick white bar. So they basically placed these in areas where other wood pigeons were gathering, and they looked to see if other wood pigeons would pay any attention to any of these models. And here are the results. They looked at the amount of time that these other pigeons spent near these models. They actively avoided, because 50% is chance, okay, that's the dashed line. They actively avoided the ones that had white on the wings, and especially that exaggerated one with the very thick white bars over on the far right, labeled H. Supernormal stimulus, because no wood pigeon has stripes that are that thick. So basically what they found is that these the members of the same species are actually, they actually find that as a threatening stimulus when the wings are open like that. The more white, the more avoidance. Oh, I love this example. These are jewel beetles, and that is a bottle of beer.
The Australian jewel beetle. The male's mission in life is simple. Find a female and mate with her. Male jewel beetles are always on the lookout for attractive females, like this fine specimen. But what makes her irresistible? Well, that's not too complicated. She's got to be big, she's got to be orange, and she's got to be covered in dimples. Give a male all three, and she's just gorgeous. It's sex on 6 legs. But what's all this got to do with beer? Australia, a beer bottle like this is known as a stubby. And believe it or not, it nearly wiped out the jewel beetle. To this questing male, all his sexual fantasies come true when he finds a discarded stubby. It's certainly big, it's the right colour, and it's got dimples. It's everything to whip a male into a frenzy. Such a beauty doesn't, of course, go unnoticed. Before long, it's covered in rampant males, and they're not keen to move elsewhere. Something had to be done. The genuine females were just sitting around unnoticed. Try as they might, they couldn't compete. Mr. Right had taken to the bottle. In the end, it was the beer industry that came to the jewel beetle's aid. Not previously known for its wildlife conservation, it ended up saving a whole species from extinction by simply changing the bottle design. Soon, the female jewel beetles were once again the only object of the male's affections. And they all lived happily ever after.
The stubby is a jewel beetle goddess to the males. Anyway, you can see it's a perfect supernormal stimulus. It's artificial stimulus that was so much more effective than the actual females that they were nearly driven to extinction because they weren't mating with the females. The guys weren't. And so it forced the beer industry to change the type of bottle that they used in Australia. Okay, this term, innate releasing mechanism, it's often abbreviated IRM. First of all, it's totally hypothetical, even though now that, it was posed back at a time when we didn't have much data from neuroscience, like back in the 1930s and 40s. Now we do have things that could be called IRMs, though we wouldn't really use that term for actual neuroscience research. But basically what this is, additional to being hypothetical, is it's some kind of central mechanism, something inside the organism, inside its brain, inside its nervous system, that is somehow attuned to a particular type of stimulus. And that when the organism encounters that stimulus, this mechanism kicks in, the innate releasing mechanism, and releases species-typical behavior, causes species-typical behavior to occur. So it's like an input-output type mechanism inside the organism's nervous system. So here's a good example of that, or the way some people went about describing it in any event. And the phenomenon itself is quite real. So what you see here is an innate releasing mechanism, IRM, in this particular species of gull that is selecting, that is attuned to red and high contrast, but not for the color of the bird's bill or the shape of the parent's head. It's preferentially going after this high contrast red and white pencil, or whatever that is, and ignoring a model of the parent of its own species. So that's what this IRM would be selecting for, redness and high contrast, not selecting for shape of head or that red spot on the bill or anything else. So essentially that model was a lesser black-backed gull model, and you can see there's the red dot. Of course, they don't have a pencil, so it's only the mom to choose from here, and nothing to choose from. It's just mom. And you can see that by pecking that red spot, because it's red, it's high contrast, there are no other choices around, it causes mom to regurgitate food like that they can eat. It's their only way of getting nourishment. Fortunately, humans have other ways of getting nourishment. Let's look at a different species, though, the black-tailed gull. Notice its bill is different. Okay, this has red at the tip and black right behind the red. So what's going to happen if we experimentally expose a chick to this, of the same species? Now, this was done by somebody else you'll hear this person trying to mimic a parental sound of a black-tailed gull. Gets pretty obnoxious after a while, but that's what this investigator was doing. It turned out the sound wasn't important at all, not too important. I think he was doing it mostly to direct the gull's attention to the actual objects that he was presenting to the gull. So here's our first clip. So notice this one has a head, that's the right shape, but it has a spot that's the wrong color. The bird is gaping a little bit. And we'll see that with almost every stimulus that is presented to the bird. But notice it's not pecking the bill. Not a single peck to the bill. It's not the right color. So doesn't care too much about contrast apparently, but the color was wrong. What's next? Well, it's very, very high contrast. It's only black now. Remember, the black-tailed gull has red and black. This only has the black. And even a fair representation of the amount of black. But no pecking. IRM says, nope, not the right thing. Don't peck. Don't release species typical of pecking. Okay, what's next? Now it's only red, and it's not even at the very tip. So it's the right color. It's at the wrong spot, and there's no black. So the IRM doesn't care about red per se either. Not when presented in that configuration at least. Now we have the right configuration, and watch the chick peck. First time we've seen that chick peck. The IRM says it's got to be red, and there has to be some black behind the red. There you go. Now, he tried altering the shape of the head to see if that was important. So here is a bizarre shaped gull head, but this only has red. So as you might predict, nothing's really going to happen with respect to the chick. It didn't like red on a normal shaped gull head. It's certainly not going to like it on this. You can see it's watching it. It's just not pecking. Species typical pecking is not being quote unquote released by an innate releasing mechanism, as it's called. Okay, what else can we try? Okay. It's the right coloration, but it's the wrong shaped head. Doesn't matter. Shape of the head doesn't matter. That red and black is what matters. Notice, though, it is the correct shape of the beak. So the shape of the head doesn't matter. But one wonders, does the shape of the beak matter? So, we'll see. That's not the shape of a beak. It's got red. There's no black. This has contrast, but no black. So we know that contrast is not the key here. This has black. It's red tipped with black behind the red. It's gaping, but it's the wrong shape. It didn't peck. So the shape of the bill is what matters, and to be sure of that, we've removed the head altogether, well, the experimenter has. Now that only has red, and again, red in the wrong place. And here we have the right configuration, red tip, black behind the red, and a beak that's shaped like a gull beak. And it's trying to peck. Get that thing a little closer. There we go. So the IRM in the black-tailed gull is selecting for the red and black configuration as well as the shape of the black-tailed gull adult beak. So those are some examples of stimuli, the terms that we use to refer to them in ethology.